Welcome. Thanks everyone for being here on time, and thanks to CoMotion for sponsoring our meetup today. So this is the CoMotion HQ. They have two other locations, and essentially CoMotion is an incubator and a community. And so if you're interested, I can connect you to some of the resources that could help start a conversation for you. And also, Mark and I would actually, do you want to come up, Mark? So Espressif and Mauser were very gracious in sponsoring us, and we're excited to have them as sponsors. And we'll actually be raffling off one of these handy Espressif ESP units. So this is an Espressif ESP-Rover. Cool. So just real quick, I wanted to kind of talk about IoT, and I think IoT was a huge buzzword probably 4 years ago, 5 years ago. And like most buzzwords, it has transitioned. It's gone through different phases. There's this idea of the Gartner hype curve. Who's heard of the Gartner hype curve? So this is a thing that comes up again and again in tech, where ideas start relatively unknown, and then at some point they achieve maximum, like, peak hype, and then they kind of follow this curve where they go through a trough of disillusionment, you know, after the hype curve, and then eventually years later they kind of plateau. There's a plateau of productivity is essentially where they end up. So things like the smartphone ended up here. Things like self-driving cars are probably somewhere over here, and so on and so forth. So this was back in 2017. This was the IoT platform, the concept of IoT as a platform. Smart dust. I have no idea what smart dust is. Anyone want to speculate? Does anyone know what's? Nice. Cool. Cool, thanks, Nick. And we're excited to have Nick here tonight. He's gonna talk a little bit about basic concepts in IoT, microprocessor versus microcontroller, things like that. So anyway, IoT went through this hype curve, and now, you know, we've come out the other end. There's this other competing curve that some of these concepts, like you know, the Segway, like what happened to Segway? And actually the Segway still exists, it's just shaped different now. But things like Betamax fall off of this version of the curve. I still think hip hop is somewhere on the curve. Anyway, so I'll let you speculate as to where IoT is on either or both of these curves. And with that, I'm gonna hand it over to Nick. Nick has been in IT for over 20 years. Sorry, I'm reading from my crib sheet here. Primarily with a background in Linux administration and network engineering, and more recently, information security. He's been an amateur radio operator for 20 years as well, and currently holds an extra class license. He enjoys fiddling with microcontrollers and embedded Linux single board computers, flying RC aircraft, playing PC games, and reading science fiction. Most recently, he's added restoration of 680 X0, is that how you say that? 68, okay, era Max to his hobbies list as well.
So what I kind of wanted to talk about today was just sort of the basics of microcontrollers and embedded systems, what differentiates a microcontroller from a microprocessor, when you'd use one versus the other, what there is in the world other than Arduino, that sort of thing. So microcontrollers versus microprocessors it's difficult to define, because one way of differentiating is you can say, okay, so microcontrollers do not have a memory management unit and microprocessors do, except when that's not the case, like the 68000 or 68020 in early Macintoshes, which had full operating systems. Or you could say, okay, so you would run bare metal code on a microcontroller, but you wouldn't on a microprocessor. You'd have a full operating system, except in cases where you don't, or where you would have some sort of operating system on a microcontroller. Typically, that's like a real-time operating system, which is more of a fancy scheduler and interrupt handler than anything else. So there isn't really a good differentiation. One tends to be more powerful than the other, except when they're not. So yeah, if you were to find, basically, one way of looking at it is this way. If it's going to end up in your smartphone or on your desk as your desktop computer, that's a microprocessor. If it's going to end up in your microwave or toaster oven, that's a microcontroller, except for the Alexa-enabled microwave. Again, exceptions everywhere. Yeah. The typical thing you would find on embedded microprocessor systems would be Linux is most common. Others you might find are QNX, which is more in the deeply embedded commercial industrial space. So it might end up on programmable logic controllers in industrial control systems, that sort of thing. Anyway, so yes, now that I've thrown this nebulous cloud at you of microcontrollers or microprocessors, let's talk about microcontrollers first. So a microcontroller will generally have a small amount of RAM and storage on the chip. Then you might have some ability to access a little bit of additional RAM or storage externally. It's going to be a lot slower to do it that way. So typically, most of it runs off of whatever's in the chip. They generally have a whole lot of peripherals of just general purpose digital I/O, I2C interfaces, SPI interfaces, UARTs, analog to digital converters, digital to analog converters. If you want to really mess with them, you connect those together and just let them have fun. Yeah, basically a whole lot of different peripherals that make them well suited to a whole bunch of ways of interacting with the world. So, you know, again, in your toaster oven or microwave, where it would have some way of taking input from a user from a whole bunch of buttons, showing a little output on an LCD or something, controlling some motors, reading some sensor values, doing stuff with all of that. Those are the kinds of places you tend to find microcontrollers. There are so many to choose from. It's ridiculous. You have your choice of, first off, 8, 16, or 32-bit microcontrollers. What differentiates those is, again, somewhat nebulous in each case. Let's say you have an 8-bit micro. It could be that the data bus is 8 bits wide, or it could be that the memory bus is 8 bits wide, or it could be that the registers are 8 bits wide, or any combination of the above. Again, the general rule is the bigger the number of your bits of a processor, it's able to work on larger chunks of data at the same time. So taking the Atmel AVR as an example, it's an 8-bit microcontroller, and it has several 8-bit registers as well as a few 16-bit registers. So if you were to do operations on a pair of 32-bit longs, adding those together, it ends up taking the least significant 16 bits of each, shoving those into a pair of the 16-bit registers, operating on those, storing that in a temporary register. Then it does the same thing on the most significant 16 bits. And then it basically just kind of takes the output of that, combines that, and then that's your output 32-bit long. So we have that 32-bit value, we're operating on it. That takes 2 full complete sets of instruction cycles to get that operation complete. So the larger the values you're trying to work on the smaller microcontrollers, the more you have to work and churn through for it to be able to process that data. So that is where the more bits, the better. 8-bit micros tend to be pretty simple devices. Another common one that you'll find is the Intel 8051, which has been around forever. And it ends up, so I think it's Cypress has some 8051 parts that have USB peripherals on them, and they run at 48 megahertz. And this is a microcontroller that when it originally was released ran at like 1 megahertz. So it's kind of funny taking the much older IP cores or processor cores and just kind of upscaling them with modern processes. So that's fun. In the 16-bit world, we have the TI MSP430, which also has a lot of DSP operations. So if you're doing any sort of signal filtering or analysis, that can work pretty well. Haven't used it myself, but that's what I hear. 32-bit is really where ARM is king. ARM has so many microcontroller IP cores, it's ridiculous. And when I say IP cores, so ARM doesn't actually make any hardware. They have designs that they license out to other companies that then produce silicon based on those designs. So they have, let me just list them off. The Cortex M0, M0 Plus, M1, M3, M4, M7, M23, M33, and M35. And most of those have a choice with or without a floating point unit, and any other number of options you can add into them. Mostly chip manufacturers will pick some set of peripherals that they will add on. NXP / Freescale, that NXP 8. You find, I think, more in automotive. And they'll have more CAN bus peripherals than other companies will. ST Micro kind of has a general round out of what they have available in their chips. So yeah, just so many. Let's see. ST Micro, NXP, Nordic, Cypress, Atmel / Microchip, because Microchip bought Atmel. Everybody's buying everybody at this point, by the way. It's ridiculous. Silicon Labs and TI, all of those produce, and more, produce ARM-based microcontrollers. Also, the Espressif ESP-8266 and ESP-32 uses an IP core from a company called, I can't remember, okay. It's either the Tensilica Extensa or the Extensa Tensilica. It's one way or the other. I don't remember which direction it is. Anyway, that's a third-party IP core that Espressif uses for that. It's a 32-bit micro that they run at, the 8266 is one core at either 80 or 160 megahertz. And the 32 is 2 cores at like 240. It's kind of insane how much power you can get out of a microcontroller these days. Similar with the ARMs, like the M7 clocks upwards of 200 and something megahertz, has a floating point unit. Crazy. So yeah. also something fun to watch out for in the 32-bit world. They're kind of a crossover between microcontrollers and microprocessors, depending on what you implement, is the RISC-V project, which is an open instruction set architecture. So with any processor, you have the instruction set architecture, which defines the set of instructions, how they're implemented, what they do, that sort of thing. Most of them, like with ARM, you would have to license or implement yourself. RISC-V, it's completely open. So you can take that ISA and build your own processor. So if any of you are so inclined, there you go. Grab the RISC-V ISA spec and your FPGA of choice and just go crazy. Or you can go grab one of the open cores that's out there, because others have done that already and produced cores that you can blow into an FPGA and play around with it. And then there's a company, Sci5, that makes a microcontroller that you can get. So that's particularly cool and nifty to watch out for as that comes up, just because having an open ISA is from the open source happy heart that I have, makes me happy. Happy. So I listed off all these microcontrollers, and maybe you're wondering, okay, what about the Arduino? The Arduino is not a microcontroller. I'm going to be exceptionally pedantic here because words have meanings. The Arduino is an ecosystem that includes a set of development boards running various microcontrollers. Those microcontrollers all have a particular bootloader on them that allows you to load code onto them easily in a particular way from the Arduino IDE. And the Arduino IDE includes a large set of libraries to be able to easily use various features of all of those different boards. So when you get the Arduino IDE, the commands that you, or the code that you would write for an ARM-based Arduino, primarily the first ones that came out were ARM-based, or I'm sorry, AVR-based, little 8-bit micros. So the code that you would write for those is the same code that you would write for the newer ARM-based ones. The libraries take care of how it's actually implemented as far as each different processor goes when you select the different board from the little drop-down. It does all the happy building in the background. Fun fact, it's actually just running GCC. So that's fun. And then you end up with whatever you want, however that little bit of code you wrote on whichever target board you have within the Arduino ecosystem. A number of third-party boards have produced board definitions and libraries that you can add in. There's the Teensy is one. Those are little ARM-based micros. They have the Teensy Duino package that you add in, and then you can program those in the same IDE. There's ESP-32 and 8266 plugins through the Arduino IDE. And these generally implement most, if not all, of the same functions that you would have with the stock Arduino experience. So this is great because it gets people up and running pretty fast, pretty easily. The downside is the way it's all the libraries are written is they're designed to get you running pretty fast and pretty easily, which means you don't have access to any of the deeper features in the hardware because they've tried to make it as general as possible. So if you want to enter a deep sleep state in one of your micros, for example, there's not a function for that. So you're gonna have to start digging in the data sheets for the particular chip on the particular board and start learning how to write to registers from the Arduino IDE, which honestly isn't that bad. You can write to registers pretty easily, and figuring out what registers to write to, if the data sheet doesn't put you to sleep right away, it's not too bad. I wouldn't say I encourage you to go do it for fun, but the more masochistic among you might, go do it for fun. So that is sort of the ups and downs of the Arduino ecosystem. It is really great for getting people into microcontrollers really fast, but you lose out on a lot of kind of the deeper, neater stuff that you can do. So as I flip my pages here, so there are other similar development environments that target a large number of boards and processors, similar to Arduino, with a large number of libraries. Some of them try to be a lot more on the kind of easy side, like Arduino is. Some of them try to be even more ridiculously easy. And then some try to kind of get a little bit deeper into things. So let's see, on the ridiculously easy side, there's CircuitPython and MicroPython, where you literally just drop a .py file onto your microcontroller and it runs it. That is, I don't think you can get any really higher level than that, other than maybe like a drag and drop JavaScript web interface, which, if it exists, don't tell me because I don't want to know. Going down a little bit, there's ARM Mbed. That one does target just ARM processors, but across a large number of boards. That one's interesting because it's a browser-based IDE, and the compiler is in the cloud. So if you want to take that offline at all, you can't. Getting the binaries onto your boards is really easy though. You plug the board into your computer and it shows up as a mass storage device, and you just drop the binary on there, and the next time it boots, it runs it. So that's convenient. And then let's see, the last one is sort of generalized, targeting a lot of systems, is called Platformio. It's at platformio.org, not to be confused with platform.io. Yeah, don't get me started on all the new top level domains. So that one has a whole lot of targets, a lot of libraries, and it doesn't have its own IDE, but it does integrate with the Atom editor as well as VS Code. So that's nifty. Also for VS Code, if you want to, there's an Arduino plugin for that. So you can get all the Arduino libraries and build system, and then try Platformio and just kind of switch back and forth from within the same IDE and see how that goes. So each individual vendor has their own tool chain as well. ST has a lot of example code. I don't really know how any of the others are. I haven't really said anything about Microchip and PIC because I don't really have any experience with them, other than anytime I see a project that's PIC-based, it is generally an electrical engineer that's done it. It's the chip of choice for EEs. I don't know why, but yeah. So let's see what else. And then GCC and Makefiles if you want. GCC supports AVR targets, ARM targets. There's I don't know if it's a patched version or what, but there is a version that comes with the ESP8266 at ESP32 dev environment. It targets that. So again, you can just write your files, write your makefile, and then build it. From there, getting it onto the board is probably the harder part, which, you know, if you're doing it at that level, you probably know about JTAG interfaces. So I'm not going to cover that. So I have pretty much talked your ear off about microcontrollers. Before I jump to the next section, does anyone have any questions about microcontrollers and microcontroller dev environments? No, nope. Do you mostly do this for work, or do you also... No, I do this entirely for fun. I have not done any of this stuff for work. By the way, any of my views and opinions expressed herein are those of mine and mine alone, and do not reflect in any way those of my employer, whom I can neither confirm or deny I do or do not work for in any way, shape, or form. Yeah. Yes. Oh, go. Go ahead.
So microcontrollers, are they more vulnerable to be hacked or less vulnerable to be hacked? I'm not familiar with them. So when you say hack, you mean like various? Oh, right. Like how do you like how easy is it to change it internally from the normal process of like putting the code on the microcontroller?
It depends. It entirely depends on how it's connected to the world and your code.
I just wanted to double check. You were talking about for environments, well, you're compiling binaries.
That is ARM embed. So that's, yeah, you drop them on as a mass storage device. Yep. About cars which?
So once again, the word hack came up this time. You say hack, you mean someone is doing something, somebody else's computer, and the third party is not intending that function. So it's likely to produce the word hack.
So.
And that's sorry, the question.
Yeah, so are they hacked?
They, I'm not clear on. So.
We hear these stories about someone is able to hack the Jeep, whatever.
Okay.
And break it.
Yeah.
And apply the brakes.
So the Jeep was connecting to it via the, I believe it was the OnStar system, GM OnStar. There was a way to connect back into the Jeep through that because it being a cellular modem, it's always online, and they didn't have any sort of, if I'm remembering it right, there wasn't any sort of protection. It was basically just on the internet. So, yeah. Other ways of getting access to car systems, there's the CAN bus, which is the controller area network that links all of the various devices in the car together. In my car, for example, there are 2 CAN buses that have a variety of safety and engine control systems on them. And both of them are connected to the Android 4.4 head unit. And none of the devices authenticate each other in any way. None of the communication is encrypted in any way. There is no anti-replay feature of anything on there. So this is why we can't have nice things.
If I remember correctly, the hackers actually had access to a vehicle prior to the instance of supposedly hacking.
I don't remember what it was that they needed in order to target that specific vehicle for the demonstration.
And I'm sorry, so the microcontrollers, Are those, they were essentially access to controllers?
They were gaining access to the vehicle communications bus that has both microcontrollers and microprocessors on it. The braking systems and such tend to be microcontrollers. They're running, so the safety critical systems in vehicles are running a variant of ARMs that are, I think it's 2 cores running in lockstep with each other. So if one fails or it gets into a wedged condition somehow, hopefully the other one carries on and doesn't plow you into a wall. So.
Thank you. Sorry. I figured out
So unlike the 737.
Oh man, that is. Does anybody here work for Boeing? Okay. It's that.
You need to cut that out.
There's a podcast I listen to called Embedded.fm, and they had an episode talking about the requirements for code that goes into aviation systems, vehicle systems, medical systems, et cetera, and all the various certifications that you have to go through for those. And we can see how still those processes can result in terrible failures. Anyway, let's move on from there.
none of those certifications are actually certified at a high level architecture.
Yeah. All right. So microprocessors or application processors. ARM, their 2 main series are the Cortex-M and the Cortex-A. M is microcontroller, A is application processor. Little naming thing. So among the application processors, there are MIPS processors. You'll find those in some lower end home Wi-Fi routers and such. They're not that common. By and far, the most common that you will see is an ARM processor. They have a just ridiculously huge range of Cortex-A CPUs. I'm not even going to try to list them all because there's just too many. Those are the things you find on the Raspberry Pi or the Banana Pi or the Strawberry Pi or the Orange Pi or the Lemon Pi or the various other clone Pis. BeagleBone, Pine 64, Friendly Elec with their Nano Pis, et cetera, et cetera, et cetera. So those have 1 or more processor cores that are running. They have 32-bit and 64-bit systems with some amount of memory. Storage is usually external on those, either through an external chip on the board or through an SD card or some other method of storage. What else do you have with those? They tend to also have video devices, so displaying video, maybe accelerating 2D video, 3D video, compressed video decode. ARM has some IP cores for those. There are also some other companies that make graphics IP cores. The unfortunate thing with the graphics engines is that for some reason, the companies that make the IP believe that releasing the documentation on them will mean that suddenly everybody will be able to completely replicate their designs and they will not have a product anymore. So tend to have binary blob drivers or not that great reverse engineered open source drivers. The newest Raspberry Pi 4, I was reading, they improved the driver situation for the graphics engine with that. So there is much less of it that is a closed source blob. They've opened up a lot of it more. So that's handy. Again, like I said earlier, the thing you'll find most on these is Linux. Sometimes you can get Android working on them. I don't know. I don't see the fun of that, but you know, it's just me. Cool thing about Linux, everything is a file. So the boards have or rather the distributions for a particular board will have a device tree overlay that defines all of the peripherals in the processor and on the board and how the OS is to address them. All of those get exposed in the /proc file system. So if you have something connected to the, say, the I2C header, you can just do a particular write out to the I2C file interface with a particular, I'd say string, but it's binary, so binary string. Anyway, chunk of data, and you can get that out to the device just by doing that. You know, just echo, yes. Oh, okay. Echo 1, redirect, proc bus, GPIO 32, enter, and the LED that you have connected to this pin suddenly turns on. So that's really cool. It makes it really easy to interface with any of the peripherals and devices on those boards. Easy to set things up, easy to find libraries for those. Most common that you find for coding for those is Python, or you can write C, C++, and get a little bit more bare metal performance. If you're writing a huge chunk of software or compiling a large set of software, building it on a Raspberry Pi really sucks. Fortunately, there are environments you can use to do cross-compilation on your desktop and then copy all that stuff over. There is even a setup, BuildRoot is the project that lets you cross-compile everything and build an entire OS image for a device, and then just load that onto the SD card for your Pi or whatever, and boom, everything you wrote, including all the bits that you decided to set up for that, right there. Running out of time, so I'm going to just kind of rush through the last section, which is connectivity. Microcontrollers don't have nearly as many connectivity options because they tend to be much lower power. They can't do quite as much, but you can still get them connected to the internet directly, which is a bad idea. Have them behind something for the love of all that is holy. So connectivity options, Ethernet, Wi-Fi, Bluetooth Low Energy, LoRaWAN, Sigfox, proprietary RF systems like the NRF 24 LO1 modules, the Hope RF modules, Zigbee, et cetera, et cetera. For a lot of those, you might have devices with a smaller, like a small microcontroller with a battery and a low power radio that wakes up every so often, sends something, goes back to sleep. And then a gateway device that's a little more powerful, that's awake all the time, listening for those, and then it will gateway that to the internet or record that or something else. So yeah, sending that off, you can go to any variety of cloud platforms or record it locally, self-hosted, et cetera, et cetera. And there are a bunch of resources on those handouts for places to buy stuff, different boards to look at, different cloud providers, different software, et cetera. So. That's it. Any other questions?
First of all, thank
Yes.
You mentioned that there, some of the microprocessors use the RTOS and the ESP-32 and I guess the 82 systems use FreeTOS. Are you familiar with it at all?
Yes, FreeTOS, yeah, that one was bought by Amazon and is being kind of actively developed and supported by Amazon. Still open source, but is sort of geared towards the, I don't know, to work out of the box with the Amazon IoT ecosystem. I don't know if that's what the ESP stuff comes with by default. It is? Okay.
So I was curious because we're trying to port some code over to it. Clearly very good with RTOS and regular
Linux, you're going to have a whole lot of syscalls available to you that you're taking advantage of. You're going to have a kernel managing your system memory, all of your scheduling, all of that. Going from a full OS to an RTOS, I'm not a developer, so I can't get too deep. Yeah, that's going to be a challenge. Make sure you got your device drivers all set up properly in the RTOS. And yeah, anything that's depending on any sort of Linux syscall, see if there's an equivalent function call in the RTOS. Ugh, yeah, it's going to be fun.
Any other questions? Then I do have a question. So do you have any projects that you said you just Presents RPi projects that you're working on right now?
Yes. So I have a CNC router. It's a little tabletop thing, and it has a DC motor. Brushed DC motor is the spindle. The speed control is just a dial that changes the amount of voltage that goes to the DC motor. So whatever speed I get it at, once it touches a material, that speed changes drastically. And when your spindle speed changes to something other than what you want it to be, and you're moving the tool at a certain speed, then the chip load on your tool changes. And long story short, I have gone through a lot of end mills. So I am making a closed loop speed controller with a tachometer that watches the spindle speed, and then we'll run a PID loop to kind of keep that at a set speed by feeding back control to the. Basically, I'll probably put a digital pot onto the speed control. PWM doesn't work with these for some reason. There's something weird going on. But yeah, so I have the tachometer working fine now. Next step is to get the speed control set and then linking them together.
And if anyone wants to follow you, post your GitHub.
Maybe Exploding Lemur on GitHub, Exploding Lemur on Twitter.
So I'm pulling?
Yes.
I'm pulling.
You're pulling.
All right, super secret number 24. Anyone? I guess you deserve it more than
Look at that.
So this is the case I got for it. It's really kind of nice and small.
Do you mind if I show off this?
Go ahead.
So is this a Pi Zero?
Yeah, it's a Pi Zero. It's got wires built into it. Where's the power source? The power source is just you use a cell phone, like a cell phone unplug it into power. You can pass this around here. This is just got out of the case, and it basically has just. I can pop open the case if you want.
You just kind of.
I've seen people online doing like trying to find out when their laundry is done. And I remember reading about this guy that used one of those sonar devices, the plugs, and based on how much energy
it's pulling through, right?
Yeah, it's going through. You can tell when the machine is running or not.
Right, that'd be awesome. And I just, my landlord is probably not as forgiving to new technology being attached to it, so I have stayed away from it. I figured these little sensors kind of sticking to a magnet, which is also another concern, is a magnet interference vibration sensor. But sticking it on there, is that going to offend them? I think it's going to be fine. A worker comes in, has to do some repairs, disconnecting, that's not a big deal. That's fine.
Yeah, I saw someone was using an accelerometer to do this, kind of the same result. That really speaks to on any given project, there's a million ways to approach it.
Yeah.
Just depends on what priorities. Everything's a trade-off.
Yeah.
So your advantage is these things cost 20 cents.
Right.
Once you've created your special software to control it, it's easy to deploy that.
And the Raspberry Pi the zeros are like $10. So the overall risk is low. And if someone comes along and steals a Raspberry Pi Zero, they're only going to see a login for my LaundryBot network, which is Twitter, hopefully, by the time it's done. So yeah, if you have any questions or if you want to look at any of the setup, I can have that for you guys afterwards. Yeah. Oh, I'm sorry? Yeah, I designed the box. I've got a box that's actually open somewhere.
Vibrate.
Yeah. It's called PET-G. It's kind of flexible. It doesn't really break. That's what a box looks like. It's pretty durable. It flexes a bit before it breaks. If you were talking about 3D printing, it's going to make its own topics another time. But I will let people have some useful things.
Can we get a round of applause?
We have PowerPoint.
I can fly through this. I can fly through it. So, because I don't want to take a ton of time on this.
There you go.
All right. So, like, I recently got interested in like 8-bit, microprocessors, retro computing and stuff. So, this is actually my very first time ever building a computer from chips. I built other stuff from chips, but not an actual computer. So anyways, I'm going to talk, like, this is kind of a very high level discussion without a lot of depth, and I kind of want to fly through it. But anyways, Z80 is a super, super old 8-bit CPU, 1976, 8 years before I was born. So it has 64K memory address space, 160 instructions. It runs really slow, which is actually kind of cool when you're flashing LEDs, because you can see everything in action. It was used in a lot of different devices in the 80s and 70s, and some still today, most notably Texas Instruments calculators, and it's still in production. So since 1976, they're still producing this chip. So here's an example of some things it was in. So our Pac-Man machines and all kinds of arcades. Sega Genesis is using the sound card. Radio Shack, TRS-80, ZX Spectrum, which I think was mostly in Britain. And again, most notably, Texas Instruments graphing calculators that mostly use Z80 CPUs.
Still today.
Huh?
Still today.
I think so, yeah. I think they're still in there. Like the more high-end Texas Instruments, I think use Motorola chips. But like a base like T84, T85, T86, that's all Z80. Yeah. So here's a pinout of the chip. So it's got an 8-bit data bus, 16-bit address bus, and it's got some control lines. The ones you use most frequently are the memory and I/O requests and reads and writes, and there's these other ones that you get used once in a while. I mean, at least that's the frequency of which I use it. I mean, I'm sure other people probably use these, different controls more or less frequently. So there's this really cool website called z80.info, and that's where this image came from. This is like a wiring diagram of like the bare minimum that you would need to get it up and running. Like not to do anything useful, but just to like, get it thinking, flash LEDs and stuff. So I made a list over there of what you absolutely need and what you can add. So what you absolutely need is you need the CPU, you need a clock, which could be a 555 timer or a crystal. Nice thing about this is you can run arbitrary clock speeds. So 555 works great if you want to run it slow or single step. You need a reset button. You need an EEPROM to read code from. You need logic chips for address decoding. So like for a certain address space, you will access, one chip, and then for another address space, you'll access another chip. And that's all done with logic gates, and you need a 5-volt supply. So that's like the bare minimum to get it going. And then of course, there's a bunch of stuff you can add to it, and it's kind of like you're limited by your imagination for what you want to put on there. There are a couple kits out there. The RC 2014 is a pretty popular one, and that's actually what I was originally going to do. And actually, somebody bought me the kit as a gift, but I thought just soldering together the kit wouldn't be a very good learning experience. It would be way more valuable to actually build it on a breadboard, which I did initially. And once I started building on the breadboard, I realized I liked that a lot more. And then eventually, what I've built here is a replica of my breadboard design in soldered form. There's also this other kit called membership card, which is kind of cool because it fits in an Altoid tin. It's actually like a little tiny thing. So that one's kind of neat. I might buy that one at some point. I've been doing exclusively assembly programming for this, and there are some good resources to learn. At z80.info, there's some really easy tutorials to get started. Also, like TI graphing calculator manuals have good resources for learning assembly. Actually, I brought a TI manual with me that has a chapter on assembly that's pretty good. There's also a really good online assembler at that website right at the bottom. A lot of the programs for assembling code are like really old and made to run off of DOS. And I was thinking about trying to get like some sort of DOS virtual machine running or something to run those programs. But I found this online assembler and I was like, no, I'm just doing that. That's so much easier. So, and then of course you'll need an EEPROM programmer because you need a way to get your code onto the chip so your computer can use it. And in my case, I'm using really old EEPROMs, the UV EEPROMs, so I need an EEPROM eraser, which is a huge pain if you make a little typo in your code, because then you got to take 15 minutes to erase your chip by shining UV light on it before you can edit it again. So I've erased the chip many, many times. So I find other ways to be productive while it's shining UV light on it. Hold on, something got screwed up. It's not going to the, wrong button, sorry. Okay, here's a list of resources. So there's this website, z80.info, which is awesome. There's this other Z80 Heaven website. There's a really cool PDF book, how to build your own Z80 computer. It's from like 1981, but it's a free PDF download and it has tons of detail. The Z80 CPU user manual is just a document you can download from Zilog's website. And then, if you get a TI graphing calculator manual, if it has a chapter on assembly programming, that's also really good and can be very useful. Okay, so I've flown through that. So now I just want to show the computer itself. So how do I? Okay, I'll let you do it. Yeah, it's flip slide. Okay, so here's I've written a few assembly programs that let me do really simple things like it can calculate prime numbers or a Fibonacci sequence, which is just every number is the sum of the previous numbers. And I also have a waveform generator using a digital analog converter, and I have a little scope, so I can make sine waves and stuff. So I think first, and what I have is I have a dip switch here where I can enter just a binary number, and then it reads that. It's in a polling loop right now where it reads that and decides which program to jump to. So if I do I'll do the Fibonacci sequence first, right? I just gotta set the switch, and then I clock it into a register, and it starts running the program. So I'll do this, and so it runs that program. So was that slow enough that you can see the number as well? All right, so that works, and then I'll run it one more time. Wait, hold on. I'm sorry, I got to interrupt it first. So interrupt. There we go. Okay. So now the prime number program, I'm not going to be able to run it all the way through because it's a lot of number crunching, but I can at least get part of the way through. Like it'll do, now notice it's up to 233. That's because it only limits itself to 8-bit numbers the way I've written it. I'm not doing like 16-bit math or anything. So now I'll calculate some prime numbers. And the bigger the number gets, like the longer it takes to calculate. So I basically just came up with an assembly coding algorithm for figuring out prime numbers. So it'll go up to the biggest one's 251. But that's going to take a while, so I don't think I want to wait for it. And I'm intentionally running kind of a slow clock speed so you can like see the LEDs flashing and stuff. I mean, if I ran it really fast, I mean, it would just like fly through the numbers, you know, and you wouldn't even be able to see them.
What do you clock?
I actually don't know what the clock speed is. I have a 555 timer with some adjustable capacitors and potentiometers, so I just kind of turn the screwdriver and I'm like, oh, that's pretty good. I'll just run it that speed. and it also has a crystal I can switch to, but it just like flies way too quick. You can't even see it. So so I mean, it's probably, I mean, if I had to guess, it's probably running like, I don't know, a few hundred hertz. Yeah. Like it's super slow clock speed. It's a 555 timer, you know. So I'm gonna stop this and then switch to waveforms, so I can show off my digital analog converter. I've got this tiny little oscilloscope here, and it takes a minute to update. So in a minute, or hopefully sooner, you'll see a little sine wave come off there. You really got to be patient with this. It takes a while for this little scope to catch up. There it goes. You see that? Yes, it's got a little sine wave generator on there. So.
I'm sorry, what is connected to what here? What's the output on the TV?
Oh, I have a digital to analog converter on there.
Oh, okay.
And it's just got I've got a little port coming out to the scope. And so I can also do like sawtooth waves and square waves. So I will interrupt this really quick. And let's see here. Next I'll do a square wave. If I got that. I think it is, yeah. Okay, so it'll take a second to update on the scope display. There we go. Let's see if I can. Oops, wrong way. I'm just changing the time scale a little bit. Yeah, that's better. So I can like make square waves. I can also do a sawtooth wave, so I'll do that one next. So that should go any second. There we go. Yeah, so I mean, these are like what it's doing is it sends an 8-bit binary number to the digital analog converter. So there's like, and it splits it up into 256 different voltage levels. So if you look at it really closely, like it actually shows like little steps in the waveforms, you know, because it's like setting these hard voltage levels and then switch to the next one. What I want to do is add some analog filtering and an output amplifier so I can actually like, you know, drive a speaker or something, you know, and actually smooth out those waveforms. And like right now, that's, you know, those are all the programs I've written. So literally that's like that's all I can do right now. So I can do prime numbers, you know, basic math. I can make a few waveforms. I want to try doing other things. Like I have some UART chips I want to hook up to it. And I kind of have this pipe dream of trying to get it to talk to Bluetooth somehow. But I'm not sure how practical or feasible it is. It won't stop me from trying though. So that's pretty much it. Yeah, and I can take it apart too if you want to like see all the boards. Because it's got.
Yeah, I encourage everyone to look at this thing up close. It's beautiful.
Yeah. This is a bidirectional data bus driver. I've got buffers for the control signals. I've got my EEPROM here, a RAM chip, some more address decoding chips. This is a a latching circuit I designed. The interface is with the display board. It lets me manually clock in a single byte, and then it also displays bytes to the 7-segment display. And this board is my my digital to analog converter board for making the waveforms. And I've left some space here where I'm going to add all the analog filtering, you know, output amplifiers and stuff. So, and I've also left some space open on the memory board in case I want to add more memory chips at some point. So that's pretty much it.
So cool. Any questions for Dane?
Have you been to the computer museum in town?
I have. I love that place. Place is really cool.
Do they have a C80 computer there running?
They probably do. They probably have like a TRS-80 or something like that. I'm sure they have something there. I don't remember off the top of my head, but I'd be very surprised if they didn't.
Pretty tedious.
Oh yeah, it's super time consuming. Like,
Just keeping track of what.
I mean, you look at all these solder joints.
Yeah.
I mean, I haven't counted, but holy cow.
Your wires all the same color. Kind of like this.
Yeah, I kind of like the green on black. I think it looks cool.
Excuse me, do you use some kind of similar to
Do I what?
use simulators to see what are these?
Is there a simulator that would?
No, I don't have. I literally design circuits with like paper and pencil. And it's really not very hard. I mean, because all this stuff can be breadboarded and you can make sure it's working.
All those stuff like
Well, like, so this is a combination of, you know, stuff I've read and stuff I've designed myself. Like, I started out with that How to Build Your Own Z80 Computer book, and I kind of used that as a starting point. And then once I was kind of comfortable with the design and how to interface with the chip, then I started designing my own boards, like the display board and the board that feeds in one byte at a time. Like, that's my design, and this digital analog converter board is also my design. But this, like the actual CPU board, is, I would say it's like 80% taken from the book I mentioned, and same with the memory board. So.
Cool.
Yeah.
Thanks, Dane.
No problem.
So I guess one other thing, just a quick note. Mark's been carrying these around for the past 3 weeks. Every time I see him, he's got them with him.
Like, do you want them?
So if anyone wants to come up and check out any of the ESP boards, we've got a dozen or so boards here, and they each do something special. Some of them do touch capacitive, some of them do camera feeds. They have some kind of an Alexa-ish board. Anyway, there's some really cool stuff. If anyone wants to check it out, we'd be happy to talk about that. And so that's one idea that we had. One idea is literally having a board library. Another idea is if you have an idea for a project and you want to use a board, build the project, document it, come and speak about it, we'll give the board to you.
And since this is my first meeting, who is we?
So Mark and I, Mark Pace, I'm Ryan Moore, and we had one meeting a couple months ago. That was our first meetup. This is our second one.
So you're a meetup and you're not officially affiliated with CoMotion, right?
No.
Yeah, okay.
We're just the lucky benefactors of generous sponsors.
Yeah, cool.
Just
two regular guys.
Just two regular guys.
No.
Yeah, it'd be interesting to see a show of hands. So Nick, you said you're 100%. You know, this is your hobby, not your job. And I think for Mark and I, it's similar. I mean, is that?
It's, yeah, for me, it's a hobby. Like, I don't spend any time recently, so I've been trying to. This is the way I'm kind of like trying to keep up.
So
be like, yeah, I'm actually doing something, but I haven't really had any time recently. So talking about that.
Can we just get a show of hands? Who's here because this is their hobby? And then who's here because this is what they do for work? Okay. Interesting.
Hobby can mean different things.
Sure.
For example, Cliff and I are working on an open source C++ networking library, and I'm trying to actually port that library over to ESP-32.
Oh, okay.
So it's not a full-time job, but I mean, anyhow.
Would that then be an open source?
Yeah, absolutely.
Okay.
Yeah. So our library runs on, Linux, Mac OS, and Windows. We run on top of ASIO, and it's the ASIO port on the ESP-32 that's problematic. So we're working with them and see, but we'd love to get it running, and then that would be open source like everything else.
Do you want to do a presentation next?
Maybe when we're over, at any time, it would be a better presentation if I could show you something that actually bloody works.
Sure.
But I could at least do the ASIO demos and things like that. So,
Not about the library.
Yeah.
And connectivity in general, I mean, that's been my career, not so much with small devices, but big embedded devices or big, not.
and I certainly can speak about programming on the ESP-32, since I use the ESP.
Cool. Any other general comments? And I think we have a few minutes left. If anyone wants to stick around and network, Mark and I will be cleaning up. But any other general comments?
Thank you. Yeah, thanks.
Thank you very much.
Yeah. Glad to do it. So when's the next meetup? That's a question. Yeah, it's a good question. So, we could do this monthly if there's enough interest. I mean, who would be interested in a monthly meetup?
Interested, it's just you have to have enough material. That's always the problem.
That's fair.
I'm not sure you have enough material for everyone.
Yeah, that's fair.
And then you end up, then there's not enough material, and then the presentations aren't as good. So that's always the balance you try to.
Yeah, so we could do bi-monthly
And then
see how that goes. Yeah, it's good feedback. Any other feedback in general? And we're always available. Mark and I are available for.
Yeah,
workshop.
nice. I'm very interested in this.
Yeah.
And I don't know if you guys have bandwidth. Entry-level workshop.
Yeah, hell yeah. So Mark and I talked about that first. That was one of our early ideas. And then we started to get a little deeper and realized, well, how do you scope a workshop? And I think we're still working on what that looks like. But just hearing that there's interest in that, who would be interested in a beginner workshop?